let's consider or discuss spectral theorem. First, change of basis. So we have a linear transform P sub B and its inverse, P inverse sub B, which map a vector back and forth between its representation in the standard basis and its representation in the basis B. So you have U, which is represented in the standard basis, which is nothing but remember E1, E2, and so on for the dimension of the vector. E1 denotes 1 in the first position and zeros everywhere else. E2 denotes 1 in the second position, zeros everywhere else. Oh, standard basis. So from standard basis to the basis B, we apply P of B. And to go back from U's representation in basis B, we apply the inverse. Just to put what I just said in writing, to put this diagram in writing, and the inverse is this. Okay, that should be clear. But so which basis? Let B consist of n basis vectors, B1 through Bn. Since U sub B representation of U in B, it follows that U is a weighted sum of basis vectors in the B, and they're weighted by components of UB. That's true for your standard basis, but it's also true as you see here, right? And this is nothing but a projection matrix vector product, which we just wrote, and I just redefined. So B, the matrix B, which we previously called P sub B, projection into B, is nothing but the basis columns, the standard basis columns concatenated together. Oh, not the standard basis columns, sorry. The basis columns, the basis vectors set as a columns and concatenated together into a matrix. This basis of the linear space B transforms B back into the canonical basis. As we already established. So, similarity transforms, what are they? Consider linear transformation represented in the standard basis by the matrix A. So, before we were saying, okay, we have some basis and we have a U in standard basis. How does U look in this new basis? Now we're saying, okay, we have a transformation A in standard basis. For example, this transformation rotates everything I don't know, 20 degrees. How does this transformation look in these bases? So we want to go from a transformation in the standard canonical basis into transformation that has equivalent effect when everything is represented in the basis B. So here's what we do. Transformation in the standard basis when applied to U results in AU. We can take we can take this AU and transform it or project it into the B basis by multiplying with B inverse. And we have this transformation as well. We know that from U back to B, from U in the B represented in the B basis back to canonical basis is just applying B. So we want to know what is A sub B, or a transformation that takes transformed version of U and turns it into transformed version or representation of a U in the B basis. Okay, you may already see what's going on. How can we represent? Just think about it. How can we represent? Let me change the color. Using those three matrices, we can represent this transform. Can you guess from the arrows here how to do it? Before you pause the video and try to derive it yourself before you continue. But here we go. Similarity transforms. Just to repeat, the matrix we seek maps UB into AU sub B. Ta-da! You were right when you guessed on the last slide. That's what happens. That is the transform. And the way we derived it, this is called the similarity transform. B and A are similar with respect to this basis B. And if you take this and apply it to U, B, you will see this gives you a U, and when apply A, which gives you AU, and then we apply B minus 1, which gives you AU in the B basis. Perfect. Similarity transform. You know now what it is and how it works. It'll be on the homework. So, but now let's think about the following. Let A be a representation of a transform in the standard basis, and let the columns of X be the eigenvectors of A. So A is symmetric. Then X and X transpose equals X transpose for the basis of eigenvectors, which are orthogonal X transpose is the same as X inverse, because X transpose X for orthogonal bases is identity. And we go from a basis of eigenvectors with an inverse from a canonical basis to a basis of eigenvectors of A with X transpose, and back from basis of eigenvectors of A into canonical basis with X. So diagonalization of symmetric matrices. So the matrix we seek maps representation of vector U in the eigenbasis of A into AU in its own in A's eigenbasis. Oh, excuse me. Well, you already figured out what it is, right? X transpose AX. Ta-da! I was right. With with an interesting property. Spectral theorem for symmetric matrices. Any symmetric n by n matrix A with n distinct eigenvalues can be factored as follows. Well, you see here, because those matrices, as we wrote on the page before, are related by similarity transform. And the matrix lambda is also n by n, and it's diagonal. X and X transpose are n by n matrices, and the ith column of X equals to the ith row of X transpose is an eigenvector of A. What does it mean to be an eigenvector? Here's the definition. All that A does to the vector, it just scales it by some value, well, some specific value, the eigenvalue of that vector. So note that xi is orthogonal to xj when I is not equal to j. So for any ij element of this product, of this matrix vector product, delta ij is either 1 if I equals to j, or 0 otherwise. And in other words, the XX transpose equals identity, and as we said, X transpose equals X inverse. Easy inverse for orthogonal basis. This property gives us this to us. So let's rewrite A equals X lambda X transpose using definition of matrix product and the fact that A is diagonal. No, the fact that lambda is diagonal. So just using a component-wise notation, we're only going through K. So I and J stay the same. This is the ith row and the jth column of X transpose, ith row of X, and just scaled by K by K. So for ijth element of A. The trick is, so I'm just writing this expression for one specific element of the A matrix, just using definition or just simply multiplying component-wise. But bear with me. So X is just vectors x1, x2, xn eigenvectors. concatenated together, right? X1, X2, Xn. That's how we get matrix X. And lambda kk is the eigenvalue that corresponds to kth eigenvector, which is ordered here. So it's a corresponding eigenvalue. Repeating what we just saw. Just look at it and think about it. But now, let's rewrite using the fact that ith. Oh yeah, we can rewrite the same expression in the following way. What is the this matrix versus that matrix when we do the product, when we compute the product? Just so you can see what we're doing. So we take first eigenvector, 0th element, second element, ith element, or rather, let's call it kth element, k1 nth element. And then the same for second, the same I'm just rewriting exactly this thing. And what we're basically doing, we take kth yeah, I messed up with the notation here. Let's call it I. We fix the I. It's fixed, you see. But we go through each of the eigenvectors. So we're multiplying this row of X matrix by the corresponding jth column of the X transpose matrix. But that's equivalently, we're fixing the element in these eigenvectors, either I or J. I'm just going through all of the eigenvectors and multiplying them by their corresponding eigenvalues. But that is the same as multiplying xk vectors in an outer product and then taking ijth element of this multiplication and summing all of them. So go through that slowly when you get a chance and do the algebra. But practically what we have here, and that's important, to compute this ijth element, we have an outer product of the same vectors weighted by corresponding eigenvalue, and then we take a corresponding element, ijth element of this outer product, and just sum up all of those ijth elements, because ijth element of this matrix is exactly this expression. The important part is that we always multiply eigenvector to itself. So the outer product here doesn't go across eigenvectors. It goes through all eigenvectors, but then we outer product the eigenvector with itself and scale it by the corresponding eigenvalue. Now the fun begins. We took our original symmetric matrix and represented it as a weighted sum of corresponding rank 1 matrices. So like in spectral decomposition of a sound, when we decompose any waveform or sound waveform into sine waves with corresponding power weighted. So we take a matrix and decompose the matrix into a basis of its eigenvector matrices of those outer producted matrices, which are all rank 1, weighted by lambda. So A becomes a product of a sum of those matrices, which are exactly the same dimension as A, and so on. So we take an A and decompose it into the basis of its eigenvectors, the outer product of those. And this is called spectral decomposition because, yeah, we compute a spectrum. Yeah, that's what I said back in the component form. The spectral factorization of A is this summation. And each lambda n times xn and xn transpose is a rank 1 matrix because it's just outer product of two vectors. Yeah, if we denote A sub I, or if we denote each component of the sum by A sub I, we know that the eigenvectors are normalized, so their inner product is 1, and we can, yeah, we can represent. Yeah, we like if you multiply through, this is 1. So that's this part of the A matrix that is comprised of corresponding element of the spectral decomposition of the matrix, and it's trivially it is trivially equals to rescaling of the corresponding eigenvector. But in the same way, you can see that lambda I xi equals, even if you take full, let's call it K. If you take the full matrix xk transpose, but you multiply each of the elements of this matrix by I, and since this is 0 for anything but k equals I, we see that the effect of the matrix A on an eigenvector is just that it's scaling. Xi is the only eigenvector of AI, and its only eigenvalue is lambda I. Yeah, well, of course, AI is a rank 1 matrix. We cannot do anything with it. Okay, so now that we have spectral theorem nailed down, we can work with principal component analysis as our next topic.